Hello, chemistry students. Welcome back to Chapter 8. This is Dr. Tullis, and we have got a huge chapter to look at. There are 9 sections we're covering in this chapter, so buckle up. Our first section is looking at Lewis electron dot structures for atoms and ions. When a chemical reaction occurs between two atoms, some of their electrons are reorganized, resulting in a net attractive force, which we call a chemical bond between the atoms. Chemists generally think of bonds as falling into 3 broad categories. We have metallic bonds, covalent bonds, and ionic bonds. Metallic bonds are delocalization of electrons around a positive nuclei. We're not going to spend any time looking at metallic bonds. We mostly focus on covalent and ionic bonds. Covalent is when there's an equal sharing of electrons between two nonmetals. An ionic bond is a complete electron transfer, and there is a metal involved. Let's look at covalent bonds first. They share electrons, and when we share electrons, only the valence electrons take part, so the outer shell electrons. Again, this is nonmetals to nonmetals. Here I have 2 chlorines. We'll look at how these dots came about in just a second. But chlorines have 7 outermost electrons, and where the 7th one is that doesn't have a pair and the 7th one that doesn't have a pair, those 2 are going to join right here, and that's called a bonding electron pair. An ionic bond is when we have ions that are formed when one or more electrons from an atom's outermost valence shell, again, are transferred from one atom to another, creating a positive and a negative ion. In this case, look, I have a sodium that has 1 outermost electron. You all remember that there's 1 outermost electron. It's going to give it away and become a +1 charge. And chlorine, we know, is in the halogen family. It has 7 outermost electrons. It would love to gain 1 more to fill that hole and become a -1 ion. Sodium, if you recall, has an electron configuration of 1s2, 2s2, 2p6, and 3s1. It has that 1 outermost electron in that 3rd energy level. It has a low ionization energy, and it will readily lose an electron to become 1s2, 2s2, 2p6, which is the noble gas configuration of neon. So it will lose that 1 electron. Chlorine, if you look at its electron configuration, it's number 17 in the 3rd energy level, 1s2, 2s2, 2p6, 3s2, 3p5. It has a high electron affinity, and it will readily gain an electron to form Cl-. If you look at this electron configuration, it now has a full p shell, and it is acting like argon. The resulting Na+ and the Cl- ions are attracted to each other by electrostatic forces, and this attraction between oppositely charged ions constitutes the ionic bond. The electrons in an atom can be categorized as either valence electrons or core electrons. Chemical reactions result in the loss, the gain, or the rearrangements of those valence electrons. The core electrons are not involved in bonding or in chemical reactions. For main group elements, which are all the A groups, the valence electrons are the S and the P electrons in the outermost shell. All of those electrons in the inner shell are core electrons. Look at sodium, put your finger on it. It's atomic number 11 in the 3rd energy level, the 1st electron. Its electron configuration is 1s2, 2s2, 2p6, 3s1. That 3s1 is my valence electron. Everything before it in the 1 and the 2 energy level, which is the same electron configuration as neon, those are core electrons. Let's look at arsenic. Put your finger on it. It's atomic number 33. It's in the 4th energy level, and its highest electron is p3. So let's look at its electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. Next is 4s2, then 3d10, and then 4p3. Its valence electrons are only those outermost s and p's because, again, it's a main group element. The core electrons is everything below that. So argon's electron configuration and 3d10. But when we're talking about transition elements, valence electrons are the outermost s and 1 less d. For example, if I said 4s2, 3d2, if I was looking at titanium. Or let's say, put your finger on zinc. Zinc's outermost valence electrons would be 4s2, 3d10. Or if it was cadmium, it'd be 5s2, 4d10. Platinum, put your finger on platinum. It would be 6s2 and 5d8. A useful way to represent electrons in the valence shell of an atom was introduced by Gilbert Newton Lewis. The element's symbol, simply by just writing the symbol, represents the atomic nucleus together with the core electrons. Up to 4 valence electrons, represented by dots, are placed one at a time around the symbol. Then, if any valence electrons remain, they are paired with the ones that are already there. Chemists refer to these pictures as Lewis electron dot symbols or Lewis electron dot diagrams. Put your finger on lithium and sodium. In my alkali metals, in my very first group, they have one outermost electron, so we depict it with one dot. Now we could also have that dot to the right, to the left, on top, or on the bottom. It doesn't matter where we have that one dot. Let's look at group 2A, beryllium and magnesium. There's 2 dots. Notice that there's one on either side. It wouldn't matter if I wrote magnesium with a dot on the right and the dot on the bottom. They just can't be paired. Then we have boron, group 3. Notice they have 3 dots, all on different sides. Carbon and silicon have 4 dots, all on different sides. Then we get to nitrogen, phosphorus, group 5. They have 5 dots. Notice that both of these have the pair on the top. It wouldn't matter if I went 1, 2, 3, 4, 5 and had my pairs on the right side instead of the top. It doesn't matter. And then we have oxygen and sulfur with 6, fluorine with 7, and notice that my noble gases are full with 8. So the basic rules, like we just said, you write the atomic symbol, that represents the nucleus and the core electrons. Treat each side as a box. Each side can hold up to 2 electrons, but we're only looking at that valence shell, remember, and we're only putting 1 per side until we need to make a pair. Let's say that this was oxygen right here. And oxygen is in group 6, it has 6 electrons. We would go 1, 2, 3, 4, 5, 6. So we do 1 per side before we double up. Arranging those valence electrons of a main group element around an atom in 4 groups is meant to convey the idea that the valence shell can accommodate 4 pairs of electrons. Because that represents 8 electrons, it's referred to as an octet of electrons. The noble gases, with the exception of helium, already have an octet of valence electrons and demonstrates that notable lack of reactivity. Those valence electrons, they are not wanting to form ions. They do not react. When it said the exception of helium, helium is the only exception where when we do 2 dots to show its outermost 2 electrons, we put them on the same side so that it looks like neon. Neon has 8, 3, 4, 5, 6, 7, 8. Notice that every side is full. There's not an electron that's by itself. Helium wants to be full on whatever side we have the 2 electrons. Because chemical reactions involve changes in the valence electron shell, the limited reactivity of the noble gases is taken as evidence of the stability of their noble gas. And the stability is showing us that they have a full S and a full P outermost electron configuration. Many elements gain, lose, or share electrons to achieve an octet of valence electrons, which again is that noble gas configuration. It's sometimes referred to as the octet rule. Hydrogen, which in its compounds has 2 electrons in its valence shell, obeys the spirit of this rule by matching the electron configuration of the helium atom. Helium we know has 2. Hydrogen has 1 outermost electron, but when it bonds with another lone electron from somewhere else, it then will have those 2, which is like helium.